quasi tutti perlomeno. Allora voglio ringraziare Celia e gli organizzatori di questa bellissima iniziativa, che questo è già il terzo anno e mi sembra, per quello che posso vedere io, un'iniziativa splendida e eccezionale che permette a giovani e anche meno giovani di imparare praticamente la cosmologia e via dicendo. Quindi ringrazio e farò del mio meglio per contribuire a questo. Ok, now I come back to English and I will talk about dark matter. The difference from what has been before, talking about the gravitational waves, is quite important. So the first thing is that gravitational wave is the very, very good success of theory. Okay? So Einstein discovered, and also from observational point of view or detectional point of view, has been incredible achievement. So physics was known, okay, by 100 years. Was so known that now we can use this result to have in a new territory or different physics, new physics. So we are going to use, what we learn by gravitational waves, for instance, for cosmology. Now I am talking about another thing. So it's something which was not present in our knowledge of physics. So we think we know everything with standard model of the elementary particle, with standard electromagnetism, and also standard gravity and GR. All these are able to explain almost everything, okay, in the universe, except two things. The first is dark energy, which I'm not going to talk. The second is dark matter. Then this is the difference from what it is. The other difference is the signal to noise of this effect. So we are talking about struggling about 5, 3, 2, the signal to noise exists, does exist, is a coincidence or not. The signal is 10 to 5 for dark matter, okay? They say, yeah, or even more in certain cases. So the evidence of dark matter as a phenomenon, I'm talking about phenomenon. I'm not talking about particle, new physics, I'm talking about phenomenon from observation. Is very, very complex, so there are many, many different proofs about this, and each of them has an enormously large signal to noise. And so the phenomenon is not in question. Of course, what is completely another thing. Why we use dark matter? Certainly it is at level of the universe, is a level of form structure. Why we concentrate ourselves in the case of galaxies, so already formed and seen today, is because it is one of the cases, very relaxed, in which we can better understand what is this phenomenon. Okay, so then we start. So we use galaxies because every single galaxy is a laboratory for dark matter. Okay, I start saying just about this. So dark matter, we know that is present in, say, 20% of the total mass energy of the universe, form structure. It is, for instance, seen at large scale in the clusters. So the two clusters, they pass one over the other. Dark matter pass through the luminous matter, so baryons stick together because, of course, they interact together. So this is one evidence which has nothing to do with galaxies, but is a completely different evidence of the existence of something which could be a dark particle. Then it has been looked at, the dark matter, but we will see then how our effort to detect the particle which we believe is at the ground of this phenomenon. Now, So, galaxies. Galaxies are, as I said, the main laboratory for dark matter. And we start to see the luminous matter, because before looking at the dark matter, we'll see as an effect of something which goes bad in the luminous matter. So we want to know what is the luminous matter. And we have three different, we have three different kind of laboratories. So one are spiral galaxies, in which you have a spiral disk which of stars which rotate. Then you have elliptical galaxies, so you have no disk like a sphere, no? And you have the dwarf galaxies, which you really have nothing, because there are a number of stars which we don't even understand why they stay together, because if they don't have a big halos or dark matter, they couldn't even stay together. So these are called the dwarf galaxies. So there are three different, very different situations in which we want to understand what's going on, each of them. So again, the difference, just to explain better, is due, for instance, to their surface brightness. So every galaxy can be, every galaxy can be defined by the central brightness, so the number of stars that stay for kiloparsec square in the center, and the total luminosity. And you see, for instance, the elliptical galaxy in the blue one are completely different in this plot with the dwarf, the spiral, and so on. So they are very, very different in populations, in distribution, and so on, of the luminous component. Now we go, what is dark matter at level of galaxies? Dark matter, I will say, is not that you are just anticipating rotation curve, flat rotation curve. This is not dark matter. And dark matter is not that you have a big mass in a galaxy. Again, this is not dark matter. There are counterexamples. The dark matter is this way. So you have the distribution of the total matter and the distribution of the luminous matter. So the gradient of the mass profile. So the name of the R. These two quantities, they do not match in all galaxies by an effect 10 to 5, 10 to 6. Okay? So, of course, in some cases by factor 10, in some cases by factor 10 to 6. So then you have to say that all gravity is wrong, totally, at the level of 10 to 5, or simply you have another component, because therefore, even if the derivative of the luminous matter doesn't match the derivative of the total matter, you have another component, which is called halo, and this makes this equation valid. So, therefore, dark matter is something which is seen from the derivative of the luminous matter and the derivative of the total matter. If you don't know these two situations, of course, you can't say anything. Okay? So this has to be, this is important. It's clear that in some cases it's obvious. This equation, the presence of dark matter is obvious independently of really measuring these quantities. Because, for instance, if you are very far from the center of the galaxy, therefore you know that this level is minus 1/2, the derivative of the velocity as function of the radius. And so you see instead that the velocity is not going like r minus 1/2, but it's going, for instance, constant or even increasing with radius. So therefore you know immediately that you have dark matter. But only in certain cases. In the most of the cases when you are inside the galaxy, until you don't study this equation, you cannot say that you have dark matter, that there is a phenomenon, and so on, so on. Okay? So this is important to say, because again, every time they say dark matter comes from R minus 2 densities total, or from a flat rotation curve, in most of the cases is totally wrong. Okay? So in this galaxy, in this place, the dark matter is very, very small. It's quite the opposite. So to have a big dark matter content in a galaxy, you should have a rotation curve which rise with the radius as linearly with radius. So you have a ball of dark matter. But this we will be seen immediately. Of course, there are theory simulations, and that to understand, just to say what happened, this was prepared in one of in the first edition, 2010, of the Dark Matter Day. Arrived at this point when I should talk about the theory of dark matter and also the simulations that in this theory have been fulfilled until now. But the situation now is very different, that really theory and simulation are very far from giving an objective, I would say, view of dark matter. So at this point, I will give only one few slides. The slide is that if dark matter is collisionless, so at least with respect to baryons, so with respect to electrons, okay? So therefore, then doing certain simulation, one arrives that galaxy forms. If one believes also in the inflation, one starts with a certain power law spectrum of the perturbations, and then arrives to a situation. First form a small object, then form big object, and at the end you have that the density distribution is universal, and that is given by this no. Okay, sorry. It is given by this formula, and this formula, you may know that is within the lambda CDM theory, but goes much beyond. So is also because when you are in the outer part of a galaxy, there is no really time to particles to interact themselves, because we are at 100 kiloparsec, 200 kiloparsec. In the history of the universe, they have interacted very, very little. So as we say, in the night every cat is dark, so I will say that at our region, every dark matter profile is, this one comes from, for instance, lambda CDM. So it is the profile of collisionless matter. And this is very, very proven, okay, from many, many simulations of different authors and so on. And I will give, because this will be the reference with what we obtain in real galaxy. So then how galaxy form, how is the galaxy formation, all this kind of thing. Again, this is the present situation. So it is a situation which is very complex, and one can say we know very, very little. We will see also why is this the situation. But of course, one thing is how galaxy form, one thing is what is dark matter. Okay? The two things are not so related in, let's say, 10 years ago, but now the two things can be completely different. So the fact that you cannot know how galaxy form, because until you don't know the dark matter nature. The dark matter nature, until 10 years ago, was given for granted. No? Now it's passed the time, this is not anymore. Tomorrow, okay, I will discuss more about this. For the moment, we say that we are going to study the properties of dark matter in galaxies. So, okay, the first one is to say why we study spiral galaxies, because these are how the rotation curves are extended, and this is the galaxy. So we see why they are so extended. Of course, they are not anymore the stars that contributes to this in the outer region. Here there is the gas, which is rotating. Very, very small amount of gas with respect to the stars, but still rotating in equilibrium. So you can go over this region. And when you go, as I said before, this is the prediction, okay? And this is what you observe. It's clear the discrepancy is without looking at the derivative, okay? But if you want to do here, you must go to see the derivative of the two components. But of course, outside the galaxy is evident that you have something beyond luminous matter. The halos, when you study, because we are able to study the halos through weak lensing or other things, they will be finished about here, okay? So I don't know even today. This is where the halo of the matter of this galaxy will end. So we know only the very, very small. The part where the stars are only, let's say, 1 millionth of the volume of the galaxy. So let's say that 10 to 6 is only one small region, and is the region where the stars are. But there is more important because where really objects are born. Then, okay, so we have to study the luminous matter. So the luminous matter is simple because, I say, all spirals they have this distribution, which is given by exponential and was found by Freeman in 1970. So this is important because, first of all, okay, it's universal, no? There are other things, astrophysically important, but they will not important for their matter. So I say that is just one distribution. The other thing, which is more important, that they express one length scale. So in the luminosity there is the length scale. Okay? That is the radius 3RD is the edge of the disk. So therefore, measuring the distribution, you know how big is the galaxy. So therefore, and this ratio is proportional to the luminosity. So nature has been in spiral, not very generous because has not given to spiral many free parameters, just one, the length scale. Everything is related to the length scale, which, by the way, is very easy for us to investigate. So basically, you have that if you set the luminosity or the length scale, you can study one kind of spirals. If you move this length scale from smallest values that are about 0.1, 100 parsec to the biggest one, they are about 50 kiloparsec, you can study the whole population of spirals. Okay, so therefore, changing luminosity, you study all the galaxies. This is a very important thing because it's a new thing from, astrophysics. In other astrophysical objects, like for instance stars, if you want to say, I stay nearby a star, no? I look what's going on, and I learn what's going on in these stars. So the question is, how many stars I have to look before I know for all kinds of stars, at least 90%? Okay, there are millions, because the stars are very, very different, they have different properties, and which really must be looked at because the outcome of their life is different according to their initial conditions or even evolution. So this is why, of course, there is the stellar evolution structure is a very, very big aspect of astrophysics. When we talk to galaxies, I anticipate how many galaxies you have to stay, 20 for spirals, 40 for ellipticals, and other 30 for other things. So you, of course, you have to stay there for all the history of the universe, measuring everything, okay, this is obvious, but nature has behaved in this way. I think even black holes, so even, for instance, GNs, they have enormous differences. So you learn only when you study astrophysical numbers, no? Here there is no astrophysical number. We will see 10 different galaxies chosen well. They can explain what happens in all spiral galaxies in the universe. Okay? So this is an important aspect for which we study galaxies. This compression of data appears important, especially in the spirals. In the other kind, you need more complex, so you need more study. Then, okay, so we know also the other components, baryonic components, but they are important because they are tracer of the gravitational field, but they are not important as mass component because they have only 1%, 10%. And for this issue, it's not important. For other issues, that could be astrophysical issue, they are extremely important, but we are talking about dark matter, so this is not important. Then, okay, a small thing, we are talking about kinematics. So the kinematics is obtained by Doppler effect, I think that everyone knows, and it is searched through lines, okay, that are produced from the gas or from the stars and so on. And they are obtained by radio telescopes because they are the 21 centimeter, which is the main line that produces information in the universe, and also some optical rotation curve. It's clear that to produce, while to 21 centimeter, you need the best telescope to the world to be, competitive, because, okay, the signal is, let's say, is strong, but not too much, and especially if you want to go far away, then really you need the new generation of, like ALMA and so on. Optical rotation curve, don't need big telescope. In fact, I think that none of them, I show just because they are good pictures of telescope, but they are using the telescope at the level of from 1 or 4 meters. So you don't need 10 meters telescope to get a rotation curve. In fact, it was used by a group that was found in dark matter, we'll see, by a group that used a really medium class telescope. And so this is quite interesting, no? Because dark matter was discovered by, we will see, by Vera Rubin and Albert Bosma, but they were not using the top level at that time telescope. Okay? So this is the idea. So again, a rotation curve, what is in this galaxy, the equilibrium of between the accelerations and the gravitational force is such that you have the sort of centrifugal equilibrium between mass and velocity and rotational velocity, and this is got by lines which are shifted if they go in one direction, that can be towards to the red, towards to the blue. And of course, this you have a sort of measurement which usually are on the plane of the sky, and then if you know the inclination, you have on the plane of the galaxy. Okay, this is how we get the information. Important is, I would say, that the data are regular. So the data, they must have a good resolution, they have to have small errors, so points which, data points which are near, they should have the same velocity, and points that stay on the other part of the galaxy at the same distance, they should have the same velocity. This is very, very interesting because the fact that you have a 2D models, no? In reality, when you want to go only 1D, so you have a lot of data that you can use to prove that everything is okay. Everything is okay means that you have only gravitation, which pulls rotation. Okay? So this is, I don't enter this because now it's obvious that no result depends on this one. But of course, in these 10 years, this has been a big discussion, how well are the data. Okay? So then, okay, that comes from the first one, detection of dark matter. These are the 21 rotation curve published in 1980 by Vera Rubin. And here you have a sort of mass discrepancy at the outer region, because in the outer parts, no, where you have data, then you don't have this kind of decline that you should have seen. So by eye, no, you see that there are different what you observed from what you have predicted. So, and was nothing more in the paper. Okay, so in the paper was only, so no sigmas or noise or other Bayesian inference or so on. So by eye, looking by eye, then this was, I would say not even model. She didn't even do the mass model. But it was apparent because clearly none of them, no, so they were a sort of flattish. By the way, flattish. They are not flattish, they are rising. The point is that they are very compressed over the x. No? So and therefore, again, if you compress the x, if you extend the x dimension, everything becomes flat, clear. Why this has been done? Has been done because the point is that convincing that all have similar profile, therefore the people could believe in this measurement. We are talking about 1979. So the first rotation curve were with such profile were produced in 10 years before, but they were extremely not believed in, basically from the main, I would say, from most of the astrophysics at that time and from all the opinion leaders of that time. In effect, the first discovery, one should go to Morton Roberts, several years ago, in the 70s even. But of course, people did not believe on that, and I must say I don't know why. So Vera Rubin was able to have better technology in order to get measurement from emission which were at a lower signal to noise, and so was able to go a little outside, and therefore here was more difficult to say that I don't believe in this data. And contemporaneously, it is important that there were also data from the 21 centimeter. And this is different because 21 centimeter this is the galaxy, and this is the data that you get at that time. Now we get the data which will be later, such relative. But even at that time, you had this rotation curve extended much more the radius, and so also this the radius of the disk. So this also in this case was a sort of proof, no, of the existence of something, because clearly, and all these galaxies, you cannot say that you should expect declining rotation curve. But look, some of them, they are declining. So we say, but at least some of them, they are completely flat in the outer region. Why they are flat? Because there is a sort of besmearing, because again, if the beam is almost as big as the galaxy, you will have a sort of flattish, no, profile. So everything you say is, especially in this case, it was very, very primordial, we will say, they are that, but convincing in this case, okay? So this has convinced. I want to say that, of course, the convincing was not given only by although the history is to say that matter comes from this, but in the same time, there were three other things very important in the 80s. First of all, the inflation, okay? So then if omega total is 1, then therefore at that time or omega matter, luminous matter is 0.05, so therefore omega dark matter must be, it must be something more than baryons. This was another push about this. Second, most important thing, because was taken by Jim Peebles, which has got the Nobel Prize. I don't know yet for what, because we don't know, but maybe also for this kind of studies. You cannot get galaxy formation without dark matter assistance. So we say in Italian aiutino. No, instead big help, a small help. In reality, it's a big help, is a major help. So it's not possible because we know that from the CMB, the perturbations are 10 to minus 5 at redshift 1000. Now the perturbations are 10 to 6 with respect to the background at redshift 0, and any baryon matter cannot do this. So since a baryonic matter can rise only, the perturbation can rise only after the CMB, the fact that the last scattering surface of the CMB, so from zeta equal 1000, so there is no time to form galaxies. And let's say, in the standard model, they need an helper, no, on how you got in the dark matter scenario, where the perturbation are not present in the dark matter, in the luminous matter at the beginning, but are in the dark matter. And so there is assisted formation, okay, from galaxies, from the dark matter. So this is another important thing. But the third important thing that came, maybe you will know, is that in the 80s, Russians found dark matter in laboratories, okay? There are some people in Leningrad, I think. At this time it was still Soviet Union and Leningrad, which found from oscillation the neutrino had 30 electron volt mass. By the way, the mass useful to get to close the universe. So, and this was an enormous coincidence. By the way, this one, the other two things, they were correct. This one was incorrect, of course. They were wrong, and these people never have been heard of. I don't know what happens to them. But in this time, they were a sort of push toward dark matter. Okay? So, and this push has, of course, continued and has obtained other independent proofs, like I say, the bullet cluster, like the two-point correlation functions. There are others that I will discuss slowly, and but in the sense that goes. If you are interested in dark matter in galaxies, okay, so this is important. All these things means that at the beginning the evidence were, but not so strong. Okay? So now, okay, this came only in 1996, where for the first time, incredible, so 1,000 galaxies has been studied. So the other, until 1996, they studied one galaxy by time. Of course, everyone was found that in agreement with the dark matter scenario. But for the first time, one was able to use a very big sample of galaxies of different luminosity, and what we have from the rotation curve, that not only there is not any reason to have decline rotation curve as the luminous matter will dictate. So all of them, they are completely different. Now the error bar, because we put together a lot of galaxies, the error bar is very, very small, and this is the first thing. So, and even if you consider individual objects, or you consider the coadded object, when you put together objects of the same luminosity and magnitude, the same luminosity, you see that there is a trend which comes from, okay, The trends for which small objects, which are here, they have very steep rotation curve, and the biggest object, they have a sort of declining rotation curve. So there is a shape change, okay? And this shape change is related to the dark matter content. So these ones, there is a dark matter content is very, very small. This one, the dark matter content will be very, very high. This can be studied by individual rotation curve or co-added rotation curve. Why you do the difference? So individual means that one galaxy has to be the quality itself to be able to make a model. Okay? So the point is that there are not many, okay? Especially in small objects, especially in certain cases. So at most of the, especially because you will see, we want to see the density of dark matter, not only how much it is dark matter, but how the density of dark matter is distributed in every galaxy. To do so, you need data which the level are very, very high, and only at the moment, let's say 100 objects is possible. The other thing is that you can put together the galaxy with the same luminosity, and they, incredibly, at the end, when you co-add together, the error goes to 0. So it means that what you see in individual object, like errors, so discrepancies, the internal noise, okay, or that every galaxy has, when you co-add many of them, it disappears, as is expected if the noise is statistical. And so then you can study the original one. These studies is also said that our main theory at the beginning, so that is the fact that you have, condition is called dark matter, has universal profile. So therefore you have also justified to put together galaxy, not only because when you do, you improve the statistics, but also because the theory, from the theoretical point of view, you have, that this is what you should do, actually, to test, for instance, this theory. Okay, so this was it was clear that every galaxy has dark matter. Every galaxy has a halo, which is much, much more extended than the halo that we see in stars. And at this level, the fraction of dark matter is different. Okay? So at this level, we know what we realize. We realize that there are galaxies with a lot of dark matter, and other galaxies which are very, very small, the minimum amount of dark matter they could have. And okay, so therefore there is a universal profile which one case relate luminosity, velocity, and radius. So, and then what is important that one could eventually imagine this presence just putting together the rotation curve and the Talley-Fisher. When you put together the relation of the Talley-Fisher with the rotation curve that we have, you see that all objects they stay on this curve. We will see this also later, how this is important. But this is the universality means that when you have, of course, radii in normalized units, right, the radius divided the radius of the galaxy, luminous part, and the velocity, for instance, even in the physical units, which is this case, you have that a cover, no? So then a galaxy stay on this surface, all of them. Okay? So this is something which must be, of course, understood, but most of these things they will be understood, so they will be attempted to understand tomorrow. Okay, so we go fast. Okay, this is the same curve seen from another point. Okay, so, and we have for instance, in this case, luminosity goes in this direction, and the velocity at the, normalized to the velocity at the optical radius, and radius in length scale. So again, normalized in terms of the length scale of the disk. So, and since I want just to start a little to say something which will be discussed more tomorrow, you see should be something that doesn't go well in this, because this is a luminous component, not luminosity. Radius is a luminous component. But this velocity is a component given by dark matter and luminous matter. So how comes that they are related? So this means, since the scatter is very, very small, so you can see also from this one the relation that from dark and luminous matter. Otherwise, of course, you will have different. So if the distribution of luminous matter is such in a galaxy, you can predict the luminosity of dark matter. Okay, if they don't connect each other because dark matter is collisionless, how can you expect this? Okay, so these are questions that we will try to answer maybe tomorrow. Okay, now we have to study. Okay, I stay 1 hour and then I will make a question and then the break. Can you tell me when it's 50 minutes? Okay, so now we study. We want to not only, I mean, in a very simple way, and in which you look something, you say, okay, then you can other say, okay. So we do something very, very, I would say physical, to make a model from which you can explain the data with model. Okay, let's say that the first one to do, okay, they were at the end of the 90s. So for 10 years, people have not done such a thing. So, of course, the data were not good, but still they preferred to say the mantra of flat rotation curve, okay, so it is unique distribution for all galaxies, and because they have to convince people that there is the world dark matter, okay? So only 10 years later, the people were so more, I mean, I would say courageous, and so they start also to analyze this data in terms of model. So the model we start certainly with the baryonic component. So the baryonic component is given by stellar disk, which is given certainly by, as I said before, the Freeman exponential thin disk. So we know the distribution of luminous matter in this object, with an exception. We don't know the total mass of the disk. So it is a free parameter that we want to know from the data. Instead, the length scale must be known. Okay? If you don't have a length scale measurement, you cannot do this game. Okay? So therefore, you have the dark matter. The gas contribution is possible to have directly from observation, because we know from the emission of the gas how much gas there is, and so there is no problem. It's a function that can be measured. Okay, there is a distance of the galaxy that could make a problem, because if you are very wrong in the distance, you cannot really measure the disk contribution. But let's suppose that you know the distance of the galaxy, so the term of the gas is known. So now we have the question to the dark matter halo. So for the first time, we say, okay, these rotation curves are due to the contribution of what we know and what we don't know. From simulations and from other, I think that since these rotation curves are averaged radially, so I don't care about if the model are really in spherical symmetry or not, because what I observe is the average, and so I average also theoretically, so I will have spherical halos. And now, what is the profile? Okay? So the profile from theory is the profile we have shown before. I put also the other profile, which has a core, because we will see that why one uses this empirical profile. Importantly, in the first 10 years of dark matter, I will say 15 years of dark matter, so from 1980 to 1995, all top people are used for halo. There were not many studies, but all the studies, they use the halo, what is called the pseudo-isothermal, including people which were the leader on astrophysics and cosmology at that time, like Bachelor, for instance. So this was what in the 15, so they were completely not taken by theoretical prejudice, and they used this because they fitted the data. So then you have a certain number of publications until 1995, in which the dark matter halo is taken by this one, the pseudo-isothermal, because as an empirical law. In 1996, it came out this NFW profile they are shown before, and since then, okay, this has been abandoned, and everyone has, for at least 10 years, used the NFW profile, which was coming out by simulations. And a profile which I will say, if you think that the dark matter is collisionless neutralino, is the profile to use, okay, without any doubt. So, but now we take another view here. So we are measuring distribution of matter in galaxies. So therefore, we don't have any kind of assumption. So we'll try all of them. So we can try both NFW profiles, and we can try some profiles which are different, so more similar to the one which were used before earlier. So came this Burkert profile, which at a large scale converges to the Burkert profile, to the NFW profiles, also because one thinks that at a large scale the matter is collisionless, and but at small scale has the possibility to have a core. So that goes to density constant. If you assume this, you don't prejudice everything, because if you find R0 equal 0, this will be almost the NFW profile that I showed before. So using this one, and as a free parameter ρ0 and R0, one keep, all possibilities that one can have. So the idea is, therefore, one uses data. Data are individual galaxies which have very, very high quality rotation curve, or quadratic galaxies which have, again, high quality rotation curve by construction. We make a model with 3 free parameters, of which one will tell you how much is the disk mass, the fraction between the disk mass and the dark matter. Another will tell you the central density. Another one will tell you the scale length, R0. Of course, if the central density will go towards to infinite, R0 will go to 0, it's clear that we will have a proven, okay, the NFW profiles. So therefore, this is the solution for the quadratic rotation curve. We will see, first of all, we are able to fit perfectly the individual, now I've shown the quadratic rotation curve, with this simple model. The model has, as I said, the 3 parameters. The model passes through all points, although the error bar is about 1%, 2%, the error bar. And one has, first of all, that small object, as I said, is completely dominated by dark matter. Then galaxies with sort of average luminosity, they are half and half dark matter. And the biggest galaxies, they are completely dominated by luminous matter, and the dark matter enters all in there. All of them, they have a core, okay? And so the core is about related to the length scale. Now I say like that, but then we'll see what happens tomorrow. And most importantly, at the end, when you do this for the 11 different coordinate curve, one has exactly this, so that luminosity, fraction of dark matter, central density, core radius are all related. So therefore there are 6 parameters volume that is very well reproduced by the line. A line in a 6 parameter volume. And okay, so we will see what this means. Certainly means that luminosity is the main or optical velocity. Any parameter that you choose on the galaxy represent all galaxy. So therefore the mass distribution is unique. It runs, okay, for in spiral galaxies, runs one over the other, just changing this parameter. Okay, this is very, okay, important, and but I will say it is, one could say, you have applied this coaddition, okay, and the procedure, which is very, very, I mean, reasonable, but let's say the same thing for individual rotation curve. So there are other people, they have done this, respect this was Cormendi and Friedan, and you see the relation between rho zero, the density, and the surface density, so the quantities rho zero times R zero and as function of rho zero, and you find individual okay. So you find the prediction from individual object and the prediction, so the finding from individual object, the relationship obtained from these 40 objects, and the lines obtained by coadding 900 objects. You see that in first approximation they coincide, and of course there is a scatter individual object because the individual object, the data now have a noise, have a big noise. Not so big because otherwise you cannot fit, but anyway, some noise they have. Now the problem is very important because as we say, I talk about core radii, central density, so no, this we are going completely different from when we start. We start with the simulations, which has a cusp, and the central densities is because, of course, the perturbation, no, they are always stronger near to the center, and therefore you should find that the center, they have to have the biggest density of dark matter, and this should be in all galaxies. We see there is something which doesn't fit, no?
What happens if you have a supermassive object in the center of the galaxy?
Yes, tomorrow we will explain. Okay, we will say, certainly. For the moment I'm talking about pure cold matter, pure cold matter scenario. So with no baryons injection. With the baryons injection can change everything. Okay, we will discuss tomorrow. So out to standard, we are, is historical now. Now I am historical, I am in 2002, 2003, 2004. And at this point, so you have simulations, and let's see this universal profile that comes from simulation. Then it seems, then the universal profile comes from observations, is different, it's totally different. So therefore, one could say, I want to see this in individual objects, okay? So we lost about 10 years to this, So to show, without any doubt, in individual object, which, as I said, they are more difficult to do because the errors that they have is clearly, they are, of course, larger than when you quad together. But of course, is a question which is made, and it is important because you don't know what happens when you do the coaddition procedure. So they are being studied. This is just one of the studies about this. This is called things. So there are studies by individual galaxies with very, very big and beautiful, I would say, effective radio telescope, and in which you can have the rotation curve, which is contemporaneously. 5 minuti? Finisco qui? Ok. Okay, 5 minutes to the break, so the surprise will be after the break, and so there are contemporaneously very, very accurate, very, very extended, with a small, ok, la batteria ancora in scarica, ok, so, and so then you can investigate the mass model in these objects, okay? And as I said, the individual objects, you need, okay, the biggest, the most important radio telescope. Yeah. At that time, ULA, for instance, sometimes even ULBI has been done. And you need, of course, to have, to pass the test, then the project has been approved, and then to study this. And the result, we will see later, but what I want to say now is that until now, we have no more than 100 rotation curve like this. And we have about 3,500 quadrant, okay? So, and this is, our evidence from which we have. It may seem not too big, but we never found a galaxy without dark matter, okay, in any case. So actually we are looking, we want to see something about second order, the derivative of the second order of the velocity to get the density. But as far as the dark matter is present in all galaxies. So I stop here, this first part, okay. Yes, question. Please don't do question on the second part because then we so question until now.
There were some observations about some galaxies, apparently they call it lost or something like that, where the dark matter was lost by these galaxies. And this is true, this would perhaps rule out this alternative models of one. I don't know if you have some form of
Okay, so when I said here, I was talking about spiral galaxies, no? So maybe I was not clear to say, when I say this is for other kind of object, the conclusion is not so clear. And also, I know it is interesting that there are few objects in which it seems that they are lacking of that matter also. So this is something which will add more spice to the question. I was just talking about spiral galaxies. So yes. I will talk about elliptical galaxy later on.
I think this is great.
Okay.
So we will take 5 minutes for break.
Anche also, I have to change.
You have to change computer. Then
Yes.
they have the
Okay.
the
Can you
if
ask?
not, we can
Okay,
change.
okay. Yes.
Okay. In cosmology, we have the Friedman equation, right? So we have omega that describes different fluids. So why can we assume that the best value to dark matter is like baryonic matter? I mean omega equal to 0. Why can we assume the same value to baryonic matter?
Because we have the CMB perturbation.
Okay.
The day when you look at the perturbation of structure, you see that the matter.
Do you have the entrance? Because this one is from here, from America, but I need the other one, like the little box. I mean, that one, that one. So
Let's
yes.
see.
Yep.
Let's see.
Yep. So yes.
Sorry.
Yeah.
Okay. So when you look at the CMB, cosmic background radiation perturbation, so they have a sort of they have 11 peaks.
Okay.
All these 11 peaks can be modeled very, very easily. Oh, see. Okay.
I can check if this is charging. I mean, I am going to open.
Okay. Yes. I hope open. Yes.
Is charging? Or not? Or how would you? Yes.
No. If charges, yes, it's
Yes,
charging.
okay.
It's
Excellent.
charging. Okay. Sorry. And okay. So you can discriminate the omega matter from omega baryons.
Okay.
Because they are different. So baryons interact with the photons, matter not. And you have 24%, 6%.
Yeah.
So this is why we know that this now we know.
Okay. Okay. I asked you that because I saw that, for example, in the cake graphic, we have the lambda CDM model, and it describes cold dark matter and dark energy, right? So when you use your Friedman equation, you assume that the best value to dark matter is like baryonic matter, omega equal to 0.
0.06.
0? No, 0.
No, the baryon, they cannot be 0.24.
Okay.
They cannot be.
No, cannot be. So I mean the state equation says that omega is equal to 0 to dark matter.
Okay.
And it's like baryonic matter.
But you cannot do this because from the perturbation you need to have omega matter 0.2.
Okay.
24.
Okay.
This is nothing to do with galaxies, but
Okay.
in the end
Okay.
you must do this.
Okay.
Okay?
Okay. Thanks a lot.
Now you have problem. I have to extend the screen, strangely.